Hello from London. Hi, I'm Kevin, a software engineer with 20 years experience. I'm one of the co-founders of Peergos. We have built a secure and privacy-focused online space to store, share, and communicate. This talk will introduce Peergos. It will expand on the project's architecture and some of the technical details. It will provide a walkthrough of some of the current functionality and a sneak peek of what the future may hold. Our vision of Peergos is to build a private web where end users are in control of their data. It is fully end-to-end encrypted, peer-to-peer, with fine-grained access control, strong metadata protection, and all of it is completely open source. To provide some context on what we have built, this slide displays the landing page when you log into a Peergos account. It looks like any other cloud storage workspace. Peergos is a friends network. This means you have the concept of following and followers. Later I will talk about how content is shared with others. I should also point out that the file system can be mounted via Fuse, and we also have a command line interface as well. The last part of the talk titled Self-Certifying Web Protocol deserves some explanation. Self-certifying means the data verifies itself, so you don't need to trust the server. It is achieved through the use of keys and hashes to cryptographically assert a user's control over their identity and data. From a user's perspective, all seems standard. You have a username, critically human readable, and a password which you can use to log in. An important property is that a Peergos client has a user-controlled identity. In practical terms, that means a user can log in from any device, a user can log into any Peergos instance, a user can migrate their data and friendship graph to another Peergos instance. Now I will briefly discuss some of the components involved as displayed on this slide. Content address storage means data is referenced by its cryptographic hash. Mutable pointers are public key to signed hash mappings. Initially, each user's file system is under a single public key. Additional keys are generated when granting write access. The mutable pointers are stored on the user's home instance. Public key infrastructure. A global append-only log for the username to identity public key, storage public key mappings. The PKI data itself is stored in the content address store. This slide introduces the login flow. Login generates a symmetric key and login key pair. The auth key pair allows you to retrieve the encrypted entry data from the server. When decrypted with a symmetric key, the result is the identity and social key pairs, plus file system root capability. Every Peergos instance is paired with an embedded IPFS instance. The interplanetary file system is a peer-to-peer protocol and network for storing and sharing data in a distributed file system. This gives us content addressing and a public key-based routing and a DHT for storing data. IPFS peer-to-peer streams is a feature which lets you create a TCP socket between any two IPFS instances. We implemented a new HTTP endpoint on the IPFS gateway, which allows you to proxy a HTTP request to any target IPFS instance who is listening using these peer-to-peer streams. To reduce the surface area of IPFS for our needs, we've built IPFS Nucleus. It only implements the 7 API calls we need, plus the aforementioned peer-to-peer HTTP proxy. It's a very thin wrapper around libpeer-to-peer and BitSwap, the internode block transfer protocol. Another important addition made is block-level access control. All content on IPFS is publicly available, even if the data is encrypted. If the encryption algorithm is ever broken, then all the data becomes public. We built on BitSwap to add an auth token, hence BAT or block access token. The authorization scheme is the same as Amazon S3. This has the benefit of being post-quantum, as it only relies on HMAC SHA-256. At this point, I will talk about the architecture on this rather busy slide. Each user has a home storage server that is responsible for storing the user's data, plus they can have multiple live mirrors. Each user has an encrypted mailbox for friend requests stored on the home server. Follow requests are blinded, so the servers cannot see who sent it. Reading them is guarded by auth to mitigate against someone logging them all now and decrypting them with a future quantum computer. Follow requests contain no unencrypted data visible to the network or server apart from the target user. Only the target user can decrypt the follow request to see the sender. Your friend list is kept encrypted in your own Peergos space. The Peergos server also includes a fully concurrent garbage collector, which is transaction aware and with no global locks. The job of the PKI server is to ensure unique usernames, username to public identity key, and thus it is logically centralized, but we mirror the data on every Peergos server. This has 3 benefits. It allows users to do private lookups for friends' public keys without announcing to the network who they are looking up. It makes the whole system much more scalable. You only need to contact the real PKI when you are signing up or changing your identity or storage server. It improves resiliency. If the PKI server were to permanently disappear, the network could move to a new one. In regards to the box in the bottom left-hand side, some users will be comfortable accessing the hosted service, trusting DNS and SSL certificate authorities. Others may decide to run a local instance and transparently interact with users on other instances while being independent of those systems. An important property of the architecture is around trust boundaries. If data crosses one of these boundaries, then it is verified by the recipient, whether it is a hash or a signature. The client does not trust the server. A client verifies the hash of every block, written or received. This means that once you have obtained a trustworthy copy of the client, you do not need to trust the server to interact with it. The server verifies the hash of everything written to or read from IPFS. This removes the possibility of tampering at the IPFS level. We've also developed a direct S3 block store. With a direct S3 block store, the client can read and write directly to an S3 bucket after authorization from the server. In case of reads, the server signs a URL that is temporarily authorized. In the case of writes, when a client wants to upload a block, they first pre-auth the block hash with the server, which returns a signed URL the client can use to upload directly to S3. Upon upload, the S3 store automatically checks the SHA-256 hash and size of the block with what was signed. To realize the design of a global file system with access control, we took inspiration from CryptTree, a folded tree structure for cryptographic file systems. A raw file is split into 5 megabyte chunks. We pad to a multiple of 4K to keep the entropy low. Each of these are independently encrypted and then split into fragments before being stored. The chunks can't be linked together from the server's perspective. As can be seen on the slide, every file or directory has several symmetric keys associated with it, and if you want to grant access to an entire subtree or just one file, you can share with them a key and then they can decrypt the file. We have implemented the efficient revocation of read and write access by automatic key rotation for entire subtrees of files. Another extension we have made is in relation to protecting metadata. The server can't see file names, paths, file sizes, as well as properties like MIME type and modified date. This also extends to directory topology and even number of files/directories. Also, the server can't tell whether something is a file or a folder. This is in addition to hiding those who have access to a file, how many have access to a file. The point to emphasize is the access control is serverless. All the processing is done on the client and enforced by maths. If you have been following the last few slides, you will probably be asking yourself that if the server is not trusted, a lot of the code must run in the browser, and that means a lot of JavaScript code. Peergos is developed in Java. We use GWT or GWT, what used to be called Google Web Toolkit, to compile the Java code to JavaScript. GWT makes the code visible to JavaScript via annotations. As it is plain to see in the JS methods snippet, the implication of this approach is that the need to use an async programming model from Java. We have supplemented the bits of the Java JDK that GWT emulates with over 100 additional JDK classes that we require, including around I/O, date, time zone handling, and especially completable futures. Also, we made a small patch to replace GWT's byte array emulation to use typed arrays. This doubled byte array performance while more than halving memory usage. We use web crypto for SHA-256 and tweetNackle.js for other crypto primitives. Cross-platform reproducible builds are important to us. We therefore vendor all dependencies, around 10 jar files, so any historic Git commit should be buildable without any external data. We use a very simple custom replacement for Webpack written in Java, which can handle Vue components called JPack. We precompile Vue.js template using the standard Vue template compiler, but run it in a vended copy of Grail.js, which is a JavaScript implementation built on Grail VM. Having finished explaining how we realize the architecture, I will now talk about some of the features of Peergos. We support static site hosting, where a folder can be configured as a www root. It will be displayed as a subdomain. As you can see, this website is hosted on ianopoulos.peergos.me. There's no need to buy a domain name, arrange TLS certificates, or run a server to host the content. What you do get is automatic website updates and peer-to-peer authenticated delivery. Even better, you can access the site via localhost through any Peergos gateway. Introducing the social feed. As well as displaying a timeline showing what has been shared with you, the social feed includes the features you would expect like posting and commenting, etc., all end-to-end encrypted. Once you have a global file system, building an application platform is the obvious next step. We start off simple with text and PDF viewers, but we offer more. There are applications such as the calendar and to-do lists. This is the calendar. With daily, weekly, monthly views, you can export, import, filter events, configure recurring events, manage multiple calendars, share events, and indeed whole calendars. Moving along, this is a screenshot of a to-do list board. You can reorder items on a list, drag and drop items between lists, and move lists around. As you'd expect, just like the calendar, you can also share boards and make a secret link to one. At the end of this talk, I will briefly introduce on how Peergos users can add their own applications. I will now spend a bit of time highlighting some unique features of Peergos. In browsers that support it, we can stream downloads. This allows us to support downloading files larger than available memory. This has been available in any browser based on Chrome for some years. Not available out of the box in Firefox due to a 4-year-old bug, but it can be enabled via a preference flag. In the case of WebKit-based browsers like Safari, just last month a blocking bug, also nearly 4 years old, was fixed. Unknown at this stage if this will mean this functionality is available soon. Viewing videos also uses streaming where available, as can be seen on the slide. This allows us to arbitrarily seek to anywhere in a video. It is also how we create thumbnails for large video files upon upload. I should also highlight the file search on the top right of the slide. Search is all done client-side, can search on metadata including file name, modified date and file size, as well as file MIME type. The bottom left-hand corner displays a screenshot of friend verification. The friend verification uses the same protocol as Signal. It works directly from the browser using the webcam, including on mobile. In the middle of the slide, you can see a part of the sharing modal. You can choose to share files, folders with individuals or with groups. Currently, we have 2 predefined groups, namely all your friends and all your followers. The access can be read-only or read and write access. The URL shown is an example of a secret link to some content. The bit after the hash is the capability. The capability doesn't leave the client and isn't exposed to the server. Now moving on to introducing some beta features available via URL feature flags. The email bridge is a separate server component paired with the email client displayed here. The bridge will encrypt emails retrieved from an IMAP mailbox and store them in your Peergos space, as well as sending outgoing emails via SMTP. It is designed in such a way that there is no state stored in the bridge. When your email bridge receives an incoming email, the bridge will asymmetrically encrypt the email and attachments, so even the bridge can't read it, and store it in a folder in your space. When you next log in, you decrypt the email and any attachments and store them in a private folder the bridge doesn't have access to. In the other direction, newly created emails are stored as a file in your space. The bridge picks this up, sends it as a real email, and deletes the file from the outbox folder. You keep a private copy that the bridge can't read. The client also provides integration with the calendar. The email bridge setup also provides a template for integration to other systems. Group chat. This is a secure peer-to-peer chat protocol implemented on top of Peergos. The protocol protects much more metadata than existing protocols by virtue of using the Peergos global file system. Under the hood, each chat stores its messages as an append-only file. Messages are not pushed to other recipients. To send a message, you simply append it to your own copy of the chat log. Other members will then pull the message and copy it into their log next time they open the app. Messages propagate peer-to-peer from member to member. The messages themselves form a Merkle DAG with each message containing a Merkle link to previous messages. With this structure, we are able to maintain causal order. That means you only see a reply to a message after seeing the message it is replying to. Chats have members and admins. Members can invite others. Only admins can remove members other than themselves. In group chats, when a member leaves or is removed from a chat, then their access to the chat is revoked, preventing them from seeing any future messages. They will still have access to the messages before being revoked. Currently in the UI, updates are gathered via polling every 30 seconds. We do have a rough outline of how to support an inexpensive call to retrieve change notifications, which will go some way to removing this limitation. Introducing a sneak peek of future development. At the top of the talk, I mentioned the private web. The slide shows one way to think about that. We are able to render arbitrary HTML, CSS, and JavaScript stored inside Peergos. Links to other Peergos user spaces also works fine. To be clear, it is not just a standard sandbox iframe, nor does it rely on any browser plugin. On the left is a SkyMap web application I wrote over a decade ago. No changes were required to have it run inside Peergos. A proof of concept branch allows the installation of web apps constrained by a permission system defined in a manifest. The manifest can associate file extensions and/or MIME types with the application. For example, registering a media player like Winamp's WebPort for audio files, or VLC's Wasn'tPort for viewing legacy video formats. Just for fun, I integrated BoxWine, which is an emulator project I contribute to, for running arbitrary Windows 16 and 32-bit binaries. Here I'm running the Windows build of AbiWord. It is one thing to cater for HTTP GET requests, but things become much more interesting when you handle other HTTP verbs. The top half of this slide shows posting a form. Clicking Submit creates a file in your workspace, so you are in control of your data. The form data is stored in a file called survey.txt in JSON format. The bottom half of the slide shows an installable to-do list web application. It uses GET and PUT requests to store and retrieve the data from your space. The critical thing to note is all this is completely serverless. Peergos has been audited by QA53. The report is linked to from the GitHub repo, the funding of which was provided via a dev grant from Protocol Labs. The grant also enabled us to do further work on the access control. We also were part of the Elevate Accelerator at Oxford Foundry. We received a small grant from Santander for winning an accelerator competition. In 2020, we received a grant by the Next Generation Internet Program for Open Internet Renovation, NGI Pointer. NGI Pointer is funded by the European Union Horizon 2020 initiative. Last month, we were announced as one of the co-winners of the Blue Sky Satellite competition for identity link proofs. Blue Sky is a community gathered together by Twitter. I hope you enjoyed this introduction to Peergos. If you did enjoy it, please consider signing up for a paid account on beta.peergos.net. 50 gigabytes for £5 per month. Usernames taken on a first-come, first-served basis. All code in the Peergos repository is licensed AGPL. All code in the Web UI repository is licensed GPL. The repo has links for donations also. If you have design skills, we would love to get your assistance. If you have any questions, see contact details as displayed. Within Peergos, you can contact us via the feedback form or via email, feedback@peergos.org. Thank you.